Okay, let's get started. Good morning, everyone. Welcome back. So last time we discussed three-phase systems, but couldn't finish this. So we will see how to change from delta connection to Y connection, especially on the load side. And I will give you one homework problem to do the same thing on the generation side. And then that's the end of chapter 2 in your textbook. And actually, the chapter 3, 4, 5 are about transformer, transmission line, and the transmission line parameters, but we will skip those parts and jump to chapter 6, which is about power flow analysis. Okay. So, we discussed balanced three-phase system. This is better than single-phase system because using the same amount of wire, we can deliver twice power. Y connection at the load side, generation side, and delta connection at the load side. This is typical. And Y connection, delta connection. So typical example. And I think we were here. So when we want to change from delta connection at the load to Y connection, the result is simply this one. The ZY, that stands for the impedance in Y connection. That is 1/3 of the impedance in delta connection. So the derivation is like this. So this is our delta connection. The impedance Z delta. And IA, IB, IC, IA, IB, IC. And then this is IAB, IBC, ICA. And we want to change this to Y connection. So suppose the two sides have identical terminal behavior. And for the delta side, this one, we get this IA. You remember this one. Only red chalk or blue chalk. No white chalk. Okay, so IA plus ICA equals IAB from Kirchhoff law, current law. So IA equals IAB minus ICA. So, and IAB is VAB over Z delta. Similarly, ICA is VCA, that one over Z delta. So this is same to that. So Z delta is expressed like that. And for the Y side, we get VAB is ZY, IA minus IB. VAB, this one. This voltage drop is the voltage drop from here and from here. So the voltage drop here is IA times ZY. That is this one. And the voltage drop here is minus IB. The direction is this way. So minus IB times ZY. So that is this part. Okay, so you see that. And similarly, we can compute VCA and so VAB minus VCA is this minus that. So 2IA minus IB minus IC. And because this is balanced three-phase, the phase current, the sum of phase current should be 0. So IA plus IB plus IC equals 0. And so IA is minus IB minus IC. So, here, minus IB minus IC is same to IA. So this part becomes 3 times IA, or 3 times ZY IA. So yeah, that is this one. So you see that this over IA is 3 times ZY, and this quantity is already we computed here, VAB minus VCA, right? So this is the conclusion. But anyway, you will be confused. So you know how to derive that, but I'm pretty sure that you will be confused which one is 1/3 of which one. But intuitively, no. Why ZY should be 1/3 of Z delta? Just intuitively, just to remember the result. Why should it be without calculation? So here, anyway, so you see, from here to here, this is VAB, this is VAB. We have a single impedance here, but we have 2 impedance there. So just intuitively, this ZY should be smaller than Z delta. Okay, so if you think like that, ZY is smaller than Z delta, and the ratio is 1/3, okay, roughly speaking. Okay.
그럼 저 델타랑 Y랑 트랜스포메이션 하는 이유가 그 Y에서의 그 뉴트럴 라인 때문인가요?
The reason of this transformation is because using a Y connection is easier to analyze. So if you make the source side Y connection and make the load side Y connection, then you have 3 single phase circuit that shares neutral line. Actually, there is no neutral line. It's perfectly balanced system. And then you can just analyze a single phase circuit. Okay, so that makes you. Yeah, that is called per phase analysis, and that's another topic of today. Good question. So this is 3-phase transmission line. Well, the photo is not, the quality is not quite good, but you see 1, 2, 3, three lines, and also you can see this neutral line here. And actually, I think this is distribution system, not transmission system. I don't know, but we have only a few lines. And this is insulator, right? And in Korean that is called 애자. 애자 means insulator, and yeah, that words come from Japanese. Okay, so as Gunju asked, now we want to go from 3-phase analysis to per-phase analysis in a balanced 3-phase system. The reason is because everything is symmetric except the phase angle is different by 120 degrees. Okay, so it is enough to do per-phase analysis for 3-phase system, and that is valid. That is especially valid for transmission network, high voltage transmission network. But this per-phase analysis may not be valid for distribution network. The reason is because you remember I drew this diagram 2 days ago. We have a pole, we have a transformer, another transformer, and the other transformer. So we have 20.9 kilovolt, and then this transformer changes this voltage into either 380 volt or 220 volt. And if we have a factory, yeah, actually, this was what I wanted to draw last time. So then all 3 lines go to this factory because they are using a 3-phase machine, the motor, okay? But for a residential house, they are using 220 volt. And then, single line goes, this is a single phase. Okay, so this is for 3-phase load, but now I want to talk about 3 independent single phase. 220 volt. And yeah, there are some residential house. Then anyway, so we have 3 phase, but in this case, it is not easy to balance these 3 lines. The reason is because we only have a few number of loads. And maybe the number of households different. And even if they are same, the random behavior of the load consumption make the power consumption here, there are different. So typically in distribution network, we need to use unbalanced 3-phase analysis. Okay, so per phase analysis is valid for transmission network. Okay. But just for simplicity, in distribution network, we also use per phase analysis. Just assuming this is a balanced 3-phase system. That's not realistic, but please bear with me. Okay. That's the case of me when I wrote a paper 5 years ago. Okay. Sometimes it is acceptable, sometimes it's not. Okay. Anyway, so we want to discuss per phase analysis. Per phase analysis allows analysis of balanced 3-phase system with the same effort as for a single phase system. And balanced 3-phase theorem says for a balanced 3-phase system with all loads and source Y connected, then they can be separated into 3 independent single phase system. And another assumption is no mutual inductance between phases. In reality, actually we didn't discuss that, but we have a transmission line and we have a ground. Then there is some parasitic capacitance. And also there is a mutual coupling between this line, that line, and this line. Okay, but we ignore this part now. Okay, so all neutrals are at the same potential. That means even if we have the neutral line, there is no current in the neutral line because the potential at 2 points are same. I mean, when everything is balanced, the voltage here and there are same, so no current. So all phases are completely decoupled. All system values are the same sequence as sources. That is, peaks of phase occurs in the same order, A, B, C. The sequence order we've been using is A, B, C. So B is minus 20 degree difference from A. So this is called lagging. So phase B lags phase A and phase C lags phase B. And this A, B, C, this clockwise sequence is called positive sequence. And there is also a negative sequence and zero sequence, but I don't want to discuss that here. And per phase analysis procedure. To do per phase analysis, convert all delta load or delta source to equivalent Y connection. Okay? Then solve phase A independent of the other phases. You can solve phase B, phase C, but the results are same, except the phase is different by 120 degree. And then the total system power, delivered system power, is just 3 times of one phase. And if desired, phase B and phase C values can be determined by inspection. Just change the degree by 120 degree, plus or minus. Okay, and if you want, if necessary, go back to the original circuit to determine line-to-line values or internal delta values. And let's see examples about per phase analysis. Here, assume 3-phase Y-connected generator with VAN 1 volt, normalized one, and 0 degree, supplies a delta connected load. The impedance is minus J ohm through a transmission line with impedance of J 0.1 ohm per phase. So the impedance of the line is from inductor. The load is also connected to a delta connected generator. So we have two power sources, and the line-to-line voltage is blah. So, and also the line has the 0.1 J impedance. So find the load voltage and the total power supplied by each generator. So this is the problem. We have a generator, one generator, the other generator, a Y connection and delta connection. So transmission line here and another transmission line here. They have the same J 0.1 ohm impedance, and this is our load. Actually, this is a purely capacitive load. So how can we analyze this system? It looks complicated, but what you need to do is change delta connection to Y connection. Okay? So first, convert delta load and delta source to equivalent Y values and draw just a phase circuit. Okay? So you know how to do that. You change these to Y, the impedance is reduced by 3 times, right? So like that, and this is only for phase A. So rather than using minus J, that is changed to minus J over 3. And also, this is your homework problem. And this source side, we have delta connected generators, but they should be converted to Y connected generator. And similarly, here the magnitude is 1 and the phase angle is 0 degree, but when you do some math, and you will find that the magnitude is 1 over square root of 3, and the phase is shifted by minus 30 degree. Okay, that is your another homework by next Tuesday. Okay. Yeah, next Tuesday. Next Thursday will be national holiday, right? So next Tuesday you need to submit that homework, but you will have a bunch of another homeworks you need to do during the Chuseok holiday. Just for you, because we will finish chapter 2 today, you need to do some homeworks. Okay, so from these complicated circuits, that is changed to this simple circuit, okay? Then you can do this. You can compute, you can analyze the circuit. And our job is to, what was the question? Find the load voltage, V, A prime, B prime. To do that, you first need to determine the voltage here, A prime, A double prime. So I want to find V, A prime. How can we do that? Well, using the Kirchhoff current law. So here, all the outgoing current, the sum of all the outgoing current should be 0. Or incoming current, the sum of all incoming current should be 0. But here, VA prime minus this voltage over this impedance is that. And another outgoing current from here to here this is the voltage difference over minus J over 3, so that one. And this current is, we already know the voltage here, that is 1 over square root of 3, that. So VA prime minus that voltage over this impedance. And the inverse of that is minus 10J. Okay, so this should be 0. We have only a single variable, so you do the simple math, get the result, right? So VA prime is computed Well, this equation, just copy it here and just solve it, then you get this result. Okay? And VB prime and VC prime, you don't need to compute that because the phase is shifted by minus 120 degree or plus 120 degree. Okay? Then all three node voltages are computed. Then our original question was, what was the load voltage VA prime B prime? Yeah, this one. We wanted to compute this one. And VA prime B prime is simply this one is simply VA prime minus VB prime. So this minus that give you that. Okay, any questions? Easy. Okay. And we want to compute the delivered power from this power source and from this power source. That is simply computed. No, for that side, what you need to do is so SA is VA IA conjugate. So yeah, here, and 3 times of that. And VA is already, that is just 0 degree. And IA is VA minus VA prime over the impedance. Here, we know this voltage, we know this voltage, so we can compute the current. Then the VI conjugate can be computed. So that is this one. That is denoted by SY gen, the Y connected generator. And similarly, the power delivered from delta connected generator is VA double prime. And then, we know this value that is given here already. And we know that. So that minus that over that, blah, blah, blah. So computing, this is the result. Just look at the result. What do you see? Y connected generator supplies 5.1 real power and some reactive power. And delta connected generator supplies minus 5.1 real power and some reactive power. Then what do you see? Yeji, can you guess what I want to say here? 근주. Actually, the sum of these two active power is 0. Why is that? The reason is because in this circuit there is no resistance. There is no resistor here. And we only have inductor and capacitor. So they do not consume real power. They do not consume active power. So the delivered power from two generators, the sum of two active power should be 0 because the load does not consume any active power, right? So the sum of these two is 0. What is real power into the load? 0. Is this a reasonable dispatch of generators? Well, this is some artificial example. What is causing real power flow from Y connected generator to delta connected generator? Actually, we can interpret this as the active power generated from here is absorbed in this generator. This generator does not generate active power, but it consumes active power that is generated from here. Okay. So this is the end of chapter 2 in your textbook. You will have some homework problems assorted from the textbook. Okay, and chapter 3 is about transformer. Transformer is important, but we skip that. And chapter 4 is about transmission line and how to determine the line impedance, the coefficient, and the coupling between the lines, but we will skip that. And another important part is the so when we discuss, if we discuss the transformer, we would discuss this concept per unit. The per unit is same to normalization. Okay, so when we analyze this power system, typically we have a generator and load and transmission line, but also we have transformer. So transformer, you know the transformer. The transformer is nothing but this is iron for the magnetic flux, heavy iron. So that's why all the transformers are heavy. You may use that kind of transformer in your home. Very heavy. That changes the 220 volt to 110 volt or vice versa. Very heavy. So when I went to United States 18 years ago, 18 years ago, just to study my PhD study, when I go to the United States, I have a big bag. It was heavy, but it became heavier because my wife put a transformer there. It was very heavy. Anyway, the transformer is heavy because it contains this iron. Okay, so N1 times of wiring and 2 times of wiring minus plus V1 minus plus V2. Then the voltage here and N1, the voltage here V2 N2. Do you know the relationship? What is that? What is the relationship between V1 and V2 in terms of N1 and N2? Is this what you say? Can somebody help me? Yeah, we are talking about ideal case. Okay, so this is possible because we are using what? This kind of transformation of voltage is possible because we are using what? No. So we are talking about AC power system, okay, from the beginning. And in AC power system, the voltage can be easily changed using this kind of simple transformer. Okay, so the advantage of AC power system is to change voltage very easily. Okay. In DC power system, the change we can do that from DC to DC. That is possible, but in that case we need to use power electronics. 전력, 전자. Okay. So the power electronics is actually all about the power conversion from AC to DC, DC to AC, AC to AC, DC to DC, 4 combinations. Okay. But in the case of AC to AC, the voltage can be easily changed using this kind of transformer. And also, so in a power system, obviously there are many transformers. some of you, most of you visited 당연히 generation, 당연히 generator. How can I say? 당연히 발전소. That is a proper noun. So, oh yeah, 당연히 power plant. Thank you. So most of you visited 당연히 power plant, and there is a big generator. But the voltage, the generator is using. It's not the voltage the transmission line uses. So the voltage need to be stepped up for transmission using transformer. Okay. And then there can be maybe the generator, the voltage, maybe like I'm not sure. Just check like this much voltage. But then using the transformer, this is stepped up like 154 kilovolt, okay, or 345 kilovolt, or 765 kilovolt, etc. So, okay, what I want to say is, anyway, we have transformers in the power system, but the good news is we can do this per unit analysis, and what is per unit analysis? That is, just normalize all the things by the amount. Just normalize the whole power system by dividing everything like 100 megawatt or 100 gigawatt, something like that. Then you get the normalized value, and that value is called PU. Okay, so that's why in power analysis, the voltage is just, the voltage magnitude is around 1.0 because we normalize that. Okay? And the virtue of using this per unit analysis is that we can eliminate transformers in this power system analysis. Okay, so when we use this per unit analysis, then we remove all the transformers. Okay, so but I skip that part, and we go directly into the power system analysis. Okay. Anyway, it makes our life easier. Okay. So here, chapter 6, this is about power flow analysis. Power system operations overview. Our goal is to provide an intuitive feel for power system operation. By the way, I ordered another power system analysis textbook, and that arrived 2 days ago. The title is Power System Generation, Operation and Control, something like that. And the textbook is used by Professor Chun Young-hwan at Hongik University. You told me that before. You don't remember, I think. So yeah, I bought the translated version a few years ago, but I ordered the original textbook, and then that new textbook has arrived. Yeah, so the advantage of using the translated version, actually the translation was done by a doctor who worked or still working, I'm not sure, at KEPCO. So all the terminologies are based on what they use, KEPCO, KPX. Well, if you study power system in English, I think that it would be easier, because Korean word sometimes hard to understand. One of the example is this one. Synchronous generators. Can you guess what it means? Yeah, in Korean this is called 동기 발전. Yeah. So we have a turbine, we have a steam, then we have a rotor, and using this FBI something, you know how the electricity is generated, and then that kind of generator is called the synchronous generator. Okay, like steam power plant or hydro power plant or nuclear power plant, all of them are based on this synchronous generator, right? So when we have a magnetic flux and we have a wire and this wire is moving in the magnetic flux, then we have electric force, induced electric force, and the current is generated. You know that? So using that mechanism is about a synchronous generator. Okay? So this synchronous means that we are talking about this AC system. So the frequency is 60 hertz. Okay? And also, yeah, 동기, synchronized. Yeah, synchronous, a similar thing. This is not a good example. You can guess what it means, but another example is that. Okay, sorry. Another example is this one. What is it? Can you guess what it means? 조상기. First name is Sangi, last name is Jo. What is it? Can you guess where we need to use this? Actually, we already discussed this before last time. Yeah, this is about the phase change by using capacitor or STATCOM or SVC to improve power factor. Okay, so 조상기, yeah, is used for that purpose. Yeah, anyway, so I will put that translate version textbook in the bookshelf so then you can refer to the terminologies. Anyway, so yeah, emphasis will be on the impact of transmission system, introduce basic power flow concepts through small system examples. Power system basics. All power systems have three major components: generation, load, and transmission, distribution. Yeah, actually, yeah, they are transmission. So the generation creates electric power. Load consumes electric power. Transmission distribution moves electric power from generation to load. So lines, transformers operating at voltages above 100 kilovolts are usually called transmission system. There is no clear definition about this. Just a rule of thumb. So over 100 kilovolt is called transmission system. And this transmission system is usually networked. Networked means here, that means, so the opposite word, yeah, I don't like this terminology, but what it says is we may have a loop, closed loop. So in a single line diagram, I draw this kind of figure before. So connection like this. We have a loop, okay? For the transmission network, transmission system, this is typical. But for the distribution system, the lines and transformers operating at voltage below 100 kilovolt are usually called the distribution system. And distribution system is usually radial or tree topology. Okay? So in radial topology or tree topology, there is no loop. Okay? Except in urban area. How many of you have used Power World already? When did you use that? Okay. What about 경영? Okay, so this Power Word was made by Professor Overby, who wrote this textbook. When he was at UIUC, he made this simulator for educational purpose. But this is a popular software, a free software, especially for the students in schools. So I will give you some small assignment So then you can use this power simulator. This is very intuitive and it supports this kind of graphical user interface. So let's see. The simplest single line diagram has one power source and one load and one transmission line. That is too simple. Typically we have three buses. So each bus has a generator and load, and they are connected like that. So using Power Word Simulator, you can change the amount of active power and reactive power of the generator and load. And what else? Loads with green arrows indicating amount of megawatt flow. Okay, so it also visualizes the direction of the power flow. And this kind of arrow is used to increase or decrease the output of the generator or load. And the direction of the arrows online is used to indicate direction of real power. Note real and reactive power balance at each bus. I will check that. And the voltage shown in normalized per unit values. Okay, so this active power, reactive power, 100 megawatt or 1000 megawatt. But voltage is always displayed as a normalized value, 1.0 pu. 1.0 pu. Sometimes this is 0.95 pu with some angle. Okay. And what is this red box? Circuit breaker. What is circuit breaker? What is the Korean word for circuit breaker? Okay. We have a similar concept that is called K. 여의, I? 폐기. So, yeah, this is a circuit breaker. Then what is it? 개폐. Open, close, open, close. So switch. So in this case, we want to change the topology. So open, close. So this kind of thing can happen at the substation. That's what KPX does. And they require to solve OPF for the dynamic topology. Okay. Then what is the purpose of this circuit breaker? So this is for operational purpose, but what is the purpose of circuit breaker? This is for safety reason. So in power system operation, sometimes overcurrent can flow. Okay, and then fire can happen, and if overcurrent flows, then we need to cut the line. That's the job of this circuit breaker. And as you see, it really breaks the circuit. And because we have a very high voltage, like 100 kilovolt or something like that, it is not easy to break the circuit. Human cannot do that. He or she would die. And also, it requires huge force. Okay. So this circuit breaker is made from some mechanical how can I say? This circuit breaker is made from some mechanical mechanism. It sounds weird, but so air circuit breaker. So there are different types of circuit breakers. Let's see that. Circuit breaker. Yeah, this is also circuit breaker, like a 두꺼비 집. Okay, you know that. But there is a huge circuit breaker. The types of circuit breaker.
A circuit breaker is an automatically operated electrical switch designed to protect an electrical circuit from damage caused by excess current from an overload or short circuit or in no load condition. In this video, I am going to show you different types of circuit breakers. Firstly, we classify the circuit breakers according to the voltage levels they can operate on. So there are three most used types of circuit breakers in this category. Number 1, low voltage circuit breaker. Number 2, medium voltage circuit breaker. Number 3, high voltage circuit breaker. Low voltage circuit breaker. Low voltage circuit breaker types are common in domestic, commercial, and industrial application. MCB, miniature circuit breaker, rated current not more than 100 ampere, trip characteristics normally not adjustable, thermal or thermal magnetic operation, breakers illustrated above in this category. MCCB, model case circuit breaker, rated current up to 2500 ampere, thermal or thermal magnetic operation, trip current may be adjustable in larger ratings. Low voltage power circuit breakers can be modeled in multi-tiers in low voltage switchboards or switchgear cabinets. Medium voltage circuit breaker. Medium voltage circuit breakers rated between 1 and 72 kV may be assembled into metal enclosed switchgear lineups for indoor use or may be individual components installed outdoors in a substation. Air brake circuit breakers.
Yeah, this is what I told you. Air brake circuit breaker. Okay. Replace oil-filled units for indoor.
Oil-filled units for indoor applications, but are now themselves being replaced by vacuum circuit breakers up to about 40.5 kV. High voltage circuit breaker. Electrical power transmission networks are protected and controlled by high voltage breakers. The definition of high voltage varies, but in power transmission, work is usually thought to be 72.5 kV or higher. High voltage breakers are nearly always solenoid operated, with current-sensing protective relays operated through current transformers. In substation, the protective relays scheme can be complex, protecting equipment and buses from various types of overload or ground or an earth fault. High voltage breakers are broadly classified by the medium use of.
What is earth fault? 지락. What is 지락? So again, we have a pole, we have a line. Sometimes the line is cut, okay, and then this line touches the ground. High voltage. This is zero voltage ground. Overcurrent flows, then fire can happen. So to prevent that kind of disaster, no circuit breaker can be used.
High voltage breakers are broadly classified by the medium used of extinguish the ARC. There are 4 types in this category. Number 1, air circuit breaker. Number 2, oil circuit breaker. Number 3, SF6 circuit breaker. And number 4, vacuum circuit breaker. Air circuit breaker. Air circuit breaker is an electrical device used to provide overcurrent and short circuit protection for electronic circuits over 800 amperes to 10,000 amperes. These are usually used in low voltage applications below 450 volt. Air brake circuit breaker, the ARC, is initiated and extinguished in substantially static air in which the ARC moves. Oil circuit breaker. Oil circuit breaker is such type of circuit breaker which used oil as a dielectric or insulating medium for ARC extinction. In oil circuit breaker, the contacts of the breaker are made to separate within an insulating oil. SF6 circuit breaker. A circuit breaker in which SF6 under pressure gas is used to extinguish the ARC is called SF6 circuit breaker. SF6 gas has excellent dielectric, quenching, chemical and other physical properties which have proved its superiority over other.
Hyung-suk, have you heard SF6 gas? No? Can you guess? Fluoride. Okay.
Other ARC quenching mediums such as oil or air. Vacuum circuit breaker. A vacuum circuit breaker is a kind of circuit breaker where the ARC quenching takes place in vacuum medium. The operation of switching on and closing of current carrying contacts and interrelated ARC interruption takes place in a vacuum chamber in the breaker, which is called vacuum interrupter. Dear sir, thanks for watching this video.
Okay, so interesting YouTube video, and that kind of circuit breaker is important. So that's denoted here by red box. Okay, actually, yeah, old technology, but important. So circuit breaker pie chart. Pie chart and numbers show real and reactive power flows, and also you see how much each transmission line is loaded. Okay, so roughly this much loaded. You can see that. Okay, and what else? By the way, so real and reactive power balance at each bus. For example, here, 106 megawatt active power and 0 reactive power. And then this generated power is consumed 100 and transmitted 2 megawatt and incoming minus 14. So the power injection is outgoing power is 60 minus 6 plus 100. That comes from here. Okay? And you can check also here. Generation is 150. So it is consumed 204, but then there is a deficit of 64, and that is 54, and that is from this line and that line, so minus 20 and minus 34, okay? So for the generator, this is the one-ohm generation and this is the one-ohm load, but for each line, when the value is positive, that means outgoing power, and when this value is negative, that is incoming power, okay? Actually, this arrow is also denotes that the direction. So here, 34 megawatt, minus 34 megawatt, okay? Any questions? Anyway, you will do some homework. Power balance constraint. Power flow refers to how the power is moving through the system. At all time in the simulation, the total power flow into any bus must be 0. You can check that here. And this is due to Kirchhoff current law. It cannot be repealed or modified. Power is lost in the transmission system. In this case, there is no power losses because the outgoing power is same to the incoming power. But typically, we have power losses in the transmission line. And if these losses are small, by the way, in power system, power losses are always used as a plural. I don't know why, but not power loss, but power losses. Okay. Power losses are small. The sending and the receiving end power may appear the same. Yeah, when shown to signal figure. Basic power control. Why this guy keep telling me about this? Oh, can I? Yeah, turn off. Okay. Basic power control. Okay. Yeah. One type of power control, power system control, is open the circuit. okay, using circuit breaker. Okay, but yeah, so opening a circuit breaker causes the power flow to instantaneously change, and there is no other way to directly control power flow in AC transmission line. So to control the power flow, we need to change the amount of generation or the amount of load. Typically, we change the amount of generation. So transmission line limits. The power flow in transmission line is limited by heating considerations. So I square R is the ohmic loss in the transmission line. These losses can heat up the line, and it causes the line to sag. Okay? And then the sagged line can touch the touch tree, and then the line. Okay, the current can flow from this line to the ground. By the way, I talked to my daughter a few weeks ago. We talked about the transmission line, and she was curious. Okay, there was you know what I want to draw, right? Three lines. You know what it is? Yeah, this is a bird. Okay. When bird sits on the line like that, it's okay, right? But if bird sits on the line like one leg here, the other leg here, then it immediately die, right? So what I want to say is, anyway, so if this line sags, it touches the tree, and then even though this is this wood is insulator, but the voltage is very high, so current can flow. Okay? Each line has a limit. The simulator does not allow you to continually exceed this limit. Many transmission owners use winter-summer limits. What does this imply? The problem of overcurrent is heat, okay? But in winter, the temperature is low. So for the same amount of current, less heat is generated. So in winter, we can, for the same line, we can transmit more power, okay? So that is called dynamic rating. The maximum capacity of the line can change over season, okay? So some transmission owners like Encore is a utility company like KEPCO in Korea of Texas. Okay. Encore are moving to dynamic rating that consider temperature. Okay. So it shows the overloaded transmission line, red, so 129%, so 29% overloaded. Okay. So overloading transmission line for a short period of time is kind of okay. But no, that is not allowed for a long time. Okay, let's talk about load model, generator model. Load models, ultimate goal is to supply loads with electricity at constant frequency, 60 Hertz or 50 Hertz, and voltage. By the way, do you know how this 60 Hertz or 50 Hertz are determined historically? Oh, how? Oh, did I post it? Maybe Kyung-Young posted it? So what does that say?
옛날부터 사용했던 철도나 장비들이
Well, one of the reasons is about the flickering of the light bulb. If the frequency is too low, human can detect the flickering of the light bulb. Okay? So the frequency should be high, but it should not be so high because high frequency the effect, one of the effect is that, so this is the intersection of the transmission line. We, just for simplicity, we assume that the current density is same across this intersection, but in reality, that's not the case. Okay? And sometimes we have surface current. Okay? So to reduce this kind of things, the frequency cannot be so high. Anyway, this is for Korea, United States, North America. This is for Europe. What about Japan? Japan is an interesting country in the sense that Japan has two power systems using 60 hertz and 50 hertz. Okay? And they are interconnected. Interesting. Yeah, there is some historic reason, but just check it on your own. Okay. Electric characteristics of individual loads matter, but usually they can only be estimated. Actual loads are constantly changing, consisting of a large number of individual devices. So using the law of large numbers, we can assume they are constant load. So in aggregate models are typically used for analysis. And two common models are constant power model. So we assume that this factory or this city or this town consumes some amount of active power and some amount of reactive power. Or another model is constant impedance model for some small component. Okay? But typically we will use this one for larger system. Generator models. Generator has an ideal voltage source, some internal resistor and inductor. So engineering models depend on the application. Generators are usually synchronous machines, typically, but these days we have power electronic device generators like a PV, solar panel. Okay, so yeah, the opposite of synchronous generator is power electronic device. How can I say? There is some terminology for that. I don't remember. Can anyone help me? Can anyone help me? The opposite concept of synchronous generator. Generation from power electronic device, like photovoltaic, the solar power generation.
Induction generator.
No. 정지 화면이 아닙니다. Yeah, there is some terminology, the generation from power electronic device. Anyway, so check it on your own. So, yeah. The important exception is the case of wind generators or solar generators. Okay, and for generators, we will use two different models. Actually, this one model, in this course, the steady state model, treating the generator as a constant power source operating at a fixed voltage. Yeah, and this model will be used for power flow and economic analysis. And another model, we won't discuss this, but short-term model treating the generator as a constant voltage source behind a possibly time-varying reactance. So it can capture dynamic transient behavior as well. Okay, power flow analysis. Let's keep discussing. We now have the necessary models to start to develop the power system analysis tools. And the most common power system analysis tool is the power flow. Sometimes that was called load flow, but no, we typically used power flow terminology. So power flow, what is power flow? S equals V times I conjugate, okay? Power flow determines how the power flows in a network, and also used to determine all bus voltages and all currents. Actually, when you have a network, node, they are connected like this, for example. There are some line impedance, okay? Anyway, if you can compute the complex voltage here, there, and there, if you know the complex voltage at each node, then everything is determined. Because the voltage at any two endpoints is specified, the complex voltage, then you can compute the current. Okay? And then based on the physics, current flows, and then you can compute the complex power at each node, each line. Okay? And because of constant power models, power flow is a nonlinear analysis technique. So this is an important one. In circuit theory or basic circuit theory, what you learn is just a linear system model. Okay, but in power system, we are using constant power model at the load side. That means our load requires some constant active power and constant reactive power. And why is that? Because they are using some power electronic devices, like your laptop. Your laptop always consumes constant power, your TV. Actually, okay, different types of load, like AC, synchronous, three-phase motors, okay? But another types of load is based on power electronic devices, laptop, computer, TV, most of the home appliances, right? So now you see why we need to have this kind of concept, constant power model. And that's the source of nonlinearity in this analysis. Okay? And power flow is a steady state analysis tool. And the opposite of a steady state is transient state. There's another big topic, and we will not discuss that in this class. So linear versus nonlinear system. You know what linear system means? Yeah, H, U, mu1, mu2. If the system is linear, you know that. By the way, when you were an elementary school student, you know the operator of addition and multiplication, right? So A times B plus C equals A times B plus A times C. Oops, you know this. And what is the name for this kind of rule? Yeah, distributive law, right? What is the rule for this? Yeah. So what I want to say here is, this is all about linear system. The very basic of the linear system. Fourier transform, Laplace transform. So, yeah. And you learned that already in your elementary school. Let me stop here. And next Tuesday, we